general, I will be interested in total properties. Total properties meaning that they are defined on all their inputs. Right? For all settings of the variables, the Boolean function is defined. Unlike, for example, the Deutsch-Joseph problem, which was a promise problem, and it was not a total property because I didn't define it on all possible settings, just the ones that were constant and balanced. Okay, so then the next ingredient that I need is multivariate polynomials, and somehow I have the feeling that you all know about this, but nevertheless I will sort of slowly go through it. And if it's going too slow, then speed me up. So in general, a multivariate polynomial is a polynomial that depends on more than one variable, like 5 in this case, and it is something, for example, x1 times x2 minus 4 times x5, 4, 5 times 3, etc. And then what you do is you plug in zeros or ones into this, into the variables, and you will get an answer. In this case, you will get, if I put in these values for the variables, you will get 0 times 1 minus 4 times 1 times 1 times 0 is also 0 plus 2 times 5 is 1 minus 4, that's this value.
We can skip.
Let me now go on. I'm already in speed up mode for you. So in particular, these things are called monomials, and the things in front of it are called the constants. And what we're interested in is the degree of monomials, which is the number of variables in such a monomial. And we can talk about the degree of the polynomial, which is the degree of the is the highest degree monomial in the polynomial.
So you don't have, for example, x squared, because you have only zeros and ones, yeah? So
yes. So on this slide. So we say a polynomial represents a function f if for all Boolean inputs the value of the polynomial is equal to the value of the function. And indeed, since I only put in Boolean values, I have that if I square my variable, it's the same as not squaring it. So I may assume that my polynomial is multilinear, meaning that there are no higher order variables. So an easy fact is that any multilinear polynomial that represents a function f is unique. There's only one polynomial that does that. Oh, actually, that's a kind of also, if you've never seen this, a good exercise. So I can actually I can define something, the degree of a function, as being equal to the degree of the polynomial that represents the function f. I can switch between these two. For example, the end function of the n variables, which is 1 if and only if all the variables are 1, is the polynomial consisting out of a single monomial. It's x1 times xn, and clearly this represents the end because it's only 1 if all of the variables are 1. So the degree of the end function is n in this setting. And for parity, you have to play a little bit, but for example, the parity on two variables you can write down as the polynomial x1 plus x2 minus 2 x1 x2, and you can verify that this is true. And in general, you can extend this and you can show that the degree of the parity is also n. In this, it will have also lower order monomials, but there will be one that has degree n. So what's the degree of the OR? Well, as you all know, that's also going to be n. And in general, for many functions, the degrees are known. So what's the connection to quantum algorithms? So why did I talk about this?
And you don't say that for every function there is unique multilinear polynomial that represents.
Yeah.
Right.
Yeah, you were not paying attention. I'm going back now. You're holding up my lecture.
I see. I'm sorry. Let's keep. Okay.
I even said that it is a nice exercise for those who do not know. So tomorrow, Koya, I want to see.
In what sense it is unique, but okay.
What?
You didn't tell us unique modular commutativity and so on. Okay.
Modular what? Commutativity?
I mean, you have to order the monomials when you
Okay.
No. I have the order of the variables, right? They have a unique name.
Okay.
Well, up to permutation of these. Okay. So it's kind of first you tell me to hurry up,
So
and then you complain that not everything is there. So I want to connect this polynomial method, or studying polynomials and the degrees of them, to studying quantum algorithms, and in particular proving lower bounds about them. And so here's a connection which I will prove, which says the following. Suppose you have a quantum algorithm that computes f exactly using t queries. We know what that means. That means that there were t of these red boxes in the unitaries. Then the amplitude on basis state I, so remember at the end of the computation you had this sum of basis states which had an amplitude in front of it. The amplitude that sits on that state can be expressed as a degree t polynomial in x. So
what is x?
X is the input x1, x2 up to xn. So in particular I can write down alpha I, that value is equal to some polynomial I that depends on the variables x1 up to xn. So if you bear with me, and I think I will prove in the next slides this statement, then we have the following easy corollary, namely that there is a degree 2t polynomial that represents f. Why is that? Well, note here we have the function f, and we know that that has to be equal, if the algorithm is correct, to the amplitude that sits on the one. Well, if f is 1, then the probability that sits on all the guys that end in a 1 in the exact case should equal 1, should sum up to 1. So the sum of these squared amplitudes is 1. And since each of these amplitudes I can compute them by means of a degree t polynomial, I get that the sum of these polynomials squared is equal to the function here and is equal to the function f. Right, so if my algorithm accepts with probability 1, then that's equal to the function, and if my algorithm doesn't accept, I reject with probability 1, accepts with probability 0, and again this polynomial equals this f of x. So this is a very simple substitution. So why is that the case? Oh, note the following corollary, that if I know a lower bound, if I know a lower bound on my degree of my function divided by 2, then I have a lower bound on the number of queries that a quantum algorithm has to make for computing that function f. So in particular you get the following corollary, that for parity and or majority, etc., since we knew that the degrees of these functions was n, you need n over 2 queries to solve them on a quantum computer. And the proof is, I just said, because the degrees are n. So actually, kind of is interesting, because remember that I told you that Grover's algorithm, this search could be done in the square root of n. Well, this simple argument proves that's something else really bad going on when you have a cell phone on in the audience. This proves that this Grover algorithm cannot be made exact. So there's inherently in the algorithm there has to be an error. So now it's kind of nice because of this correspondence, that you can plug in all kinds of results that are known about functions. For example, if you have a symmetric non-constant function, then we know that the degree of that function is going to be almost n. And it's going to be n if n is a prime. So for all these functions, you get bounds of linear over 2. By just plugging in the known results about degrees, and you get automatically bounds on quantum algorithms that solve these problems. So let me tell you the proof of this statement that says that the amplitude on each basis state can be expressed as a polynomial, which also is a simple proof. So remember that we started out with our unitary, and the proof is going to be by induction on the number of queries that the algorithm makes. So remember that the algorithm started out with all zeros and then did this first unitary, right? And then came the first oracle query. So note that after this first unitary, I can write the state again as a sum of alpha j. I can write it as a superposition of all basis states. And note that the alpha j is the amplitude that sits in front of state j. And note that I can just set the polynomial j in this particular point to be alpha j. And that's going to be independent of x, because the algorithm didn't make any query. It's purely dependent on the unitary, the first one. And that's true for all j's. So after the first unitary, there's no problem. So now comes the first query. And note that the query only changed the part of the state that queried something. So imagine that I am looking at the state I0, the basis state I0, because that was a particular basis state that queried variable I. So that basis state I0 changed into I0 plus xi. Okay, that's what the thing said. And the basis state I1 changed in I1 1 plus xi. Right, so the negation of xi. So note what happens if xi was 0. So let's consider two cases. If xi was 0, then actually I0 stayed I0, and in particular the amplitude I0 didn't change. And also the amplitude I1 didn't change, because here I got 1 plus 0, which is 1, so the amplitude stayed the same. However, if my value of xi was 1, then actually this state now will become I1, right? Because it's 0, which now has amplitude I0 in front of it. This becomes I1. So the I1 amplitude now is equal to the I0 amplitude, and likewise here the two changed, and so the amplitude I0 then becomes what I1 was, right? So if xi is 0, nothing happens. If xi is 1, then these two states, I0 and I1, the amplitude is shifted from one to the other. Okay? So that fact can be easily expressed as a degree 1 polynomial, namely the polynomial I0 now, after the query, is equal to alpha I0 times 1 minus xi, because if xi is 0, then it stays the same, plus alpha I1 times xi, because then this part is 0, and then it switches, and likewise the amplitude on 1 stays the same if xi is 0, and becomes the other one if xi is 1. Simple degree 1 polynomial, and that expresses now the amplitude on the basis states after first query. So next we apply second unitary, so now comes sort of the induction thing. So now we apply a new unitary on our new state, for which I could express all the basis states as polynomials. And note that for basis states j, because it's a linear operation, it will just linearly match these terms up. And I can write the amplitude now on basis state j as a linear combination of the previous ones. But linear combinations, it's a sum of constants times these polynomial states, a polynomial of the same degree. So after my unitary 1, the claim is true. I made one query, and the polynomials in front of the basis states can be expressed as a degree 1 polynomial. Well, etc. You can now fill out your induction yourself. After t queries, it's a degree t polynomial. End of proof. So actually, I think it's kind of neat because it's a very simple. All the things were very simple, but nevertheless, you got something that wasn't obvious at all. Certainly not at the time when we did this. How to prove lower bounds for these quantum algorithms, because they go all over the place and it's not clear what happens. I think it's nice because you can sort of translate it into something more general, because these polynomials are more general and actually provably more general, and then prove some easy fact about these polynomials, which is something you'll learn in high school, and get this nice conclusion. So I think it's a sort of a nice illustration of mathematics. So let's continue to bounded error setting, and now I have to define what it means to represent in the bounded error setting, and that is something that's called approximates. And now instead of saying that the polynomial equals to the value that the Boolean function, you say it's close to it. So it's not the absolute value difference is bounded by a third. And again, the thing is multilinear because xi squared is still xi. However, Kolja, the polynomial is not unique anymore. There may be many polynomials now that approximate a certain function. It's easy to see if you change it a tiny little bit, it still will be within a third, and that's a different one. So that's a complication. So now I have to define the approximating degree of my function as the smallest degree polynomial p that approximates f. And there may be many, but certainly there is one that has the fewest, has the smallest degree. And that's how I define the approximate degree of f. By the way, these things have been defined probably in the 60s already, so it's not my definition, but as you can find in the literature. Okay, so now there's an easy corollary, so to speak, of the proof I just showed to you, that says that if I have a quantum algorithm or a quantum computer that computes f in the bounded error setting, and it makes t queries, then the amplitude on basis state I, well, this is what I just told you, it can still be expressed as a degree t polynomial, same proof. I mean, nothing changed, only the promise that the output bit is now not 1 or 0 anymore, but 2/3, at least 2/3.
No, but now f is completely redundant in the theorem. Right?
Sorry?
So you don't speak about f more, just for any quantum setting, independently of what it computes. It's just a polynomial.
Yeah, but it's a polynomial, and if it makes t queries, it's a degree t polynomial, these amplitudes. But now note that we have that f of x minus the probability that this thing accepts is at most a third. And since, again, like before, I can substitute for this value here, I can substitute this polynomial squared. I get that this polynomial p of x approximates the function f of x. And it has degree 2t at most. Okay?
And if you replace 1/3 by 1/5, degree could change, of course.
Yeah, but I mean, you of course then also have to allow, if you want to stay in step with algorithms, the algorithm to be correct with probability 4/5 or 1/5. Right? I mean, sort of the epsilon. I mean, you could put epsilon here. And the epsilon in the polynomial and the epsilons in the algorithm should be the same, but that usually doesn't change a whole lot. Okay, so you get the immediate corollary that the approximate degree over 2 is the lower bound on the bounded error query complexity for that function. However, the approximate degree is a little bit harder to compute. However, did you not have the book Perceptrons here?
No.
Oh, I thought I saw it. Ah, okay, but I did see it. But in that book they study these questions extensively. It's nice stuff. And for example, what you can find is that the degree of the OR function is square root of n, or omega square root of n. You can just look at the proof in there from the 60s, and immediately you get that the quantum query complexity of the OR is lower bounded by square root of n. I mean, there should be constants here, but ignore those. And hence you get from this old result, you get that Grover's algorithm is optimal with the previous reason.
Was it how it was proved before?
No. No. No, it was kind of an ad hoc way of dealing with that. And this is sort of also unifying the whole area and making it sort of making a precise framework and giving a tool, an old tool, the polynomial method for getting easily getting bounds. More examples. For example, the degree of the parity, that is for sure in the Perceptron's book, is n. That is also easy to show. And it follows that the quantum query complexity of parity, the lower bound is n over 2, it follows. And actually, exercise for you guys if n is even, tell me you can devise an algorithm that computes the parity in exactly n over 2 queries. I mean, we saw that Deutsch's algorithm can compute of any 2 with one query the parity. And if I have n variables, let's assume n is even, then I can, for each pair, I can compute the parity with one query, which amounts to n over 2 queries, and then take the parity of the answers, which is the parity of the result. And this is also nice because it shows that this factor of 2 that I lost in my translation, remember I had that it's a degree t algorithm, you get a degree 2t polynomial, that is actually optimal, that is needed, because here is an example where the quantum query complexity is a factor of 2 better than the degree of the polynomial. So actually there was nothing lost in doing that. Again, the degree of the majority can be computed. It's omega n, and hence the degree of the quantum query complexity for computing majority is also omega n. So in general, you have lower bounds for symmetric functions where the upper and lower bounds are tight, because you can look at the results in the literature for these functions. And then actually what we managed to do is come up with algorithms that matched these bounds by tweaking Grover's algorithm. Okay. So in general, I want to relate the classical black box complexity, meaning algorithms that are not quantum but just randomized or deterministic, to quantum algorithms. And we have seen that actually this totality is an important thing, because we have seen that for Deutsch-Josa, well, Simons and Shor's algorithm, we had this exponential speedup. Right? We had 1 versus n over 2 or something else, but there was a promise problem. On the other hand, we've seen that for Grover's algorithm, there only was a square root of n speedup, but it's a total problem. So the question is, can you exponentially speed up total problems? Can you have these two worlds at the same time? Actually, the answer is no, you cannot. And one thing that comes out of this thing is the following. You can prove that the deterministic query complexity of f is bounded by the approximate degree of f to the power 6. So put in different words, if I have the approximate degree of my total function is f, then I can s, say, then I can in s to the 6th many steps, many queries, I can compute f deterministically. Can extract an algorithm from that. I don't have time to show that. And this was shown by Nissan and Szekely with the power 8, and well, we could improve it to 6. By the way, I don't know if the 6 is optimal. I somehow suspected that it should be 2, but nobody knows how to prove that. But as a corollary, you get that since the approximate degree was a lower bound on the quantum query complexity, you get also that if you have a quantum algorithm that computes f making t queries, then there's a deterministic algorithm that uses t to the 6th many queries. Okay, so in particular for total functions in this black box setting, you cannot have an exponential speedup. At most 6th power, and the best we know is a square, and that is Grover's algorithm. But I don't know. It would be actually interesting to show either to pull this down to a square, which I kind of suspect is the case, or come up with another problem where you have a cubed advantage. But so far nobody has done this, the second one. And you can, if you care about the exact algorithms, you can get a slightly better. Actually, I think these results now have improved to power 3. If you have a deterministic, if you have an exact polynomial that represents this thing, then you can actually find a better, only a 4th power, and I think it's a cube now. I should have looked up before this. Algorithm that uses only a cube, a 4th, and I think a cube number of queries, and in particular you also get that the exact query complexity cannot be more than a 4th power, or probably a cube better than the deterministic. But also these bounds are not known to be type. I mean, we don't know the type bounds yet.
Okay, but query complexity and degree differ by a power of 2. Why you obtain here again 4?
Query complexity and degree are different by a factor of 2.
Not factor?
Yeah. If I have t, then it's 2t.
Yeah.
So it's a factor of 2 in the degree.
I see.
Which
which
would be 2 to the 4th, which would be a
it's not square.
No, it's a constant which is hidden in the big O here.
Okay.
Okay, so these things have been extended. For example, there's other problems like the collision problem by Aronson, who also uses this polynomial method. Actually, in fact, Sasha's proof showing that the communication complexity for disjointness is square root of n, also it ultimately reduces to a polynomial of degree square root of n. And actually the last one I know is a log n lower bound for Simon's problem. I haven't talked about Simon's problem for those of you who know, but also that uses the polynomial method. I have to say though that there is a competing proposal by Ambinus called the quantum adversary method. So the adversary method is something that you could use classically. For those of you who've seen this proof, you get an algorithm and then you try to find a hard input for that algorithm that defeats it if the algorithm was too fast. And you play the adversary defeating algorithms and proving that they need many queries. So you can devise a quantum version of that, which was done by Ambinus, and then several different formulations were floating around, and they were all unified by Spalek and Szegedy in 2005. And this year there was a paper sort of really getting a better adversary method, where they had negative weights, and I guess this doesn't say much if you haven't seen the method, but so there's a lot of work along these ways, and it's shown that these negative weights indeed sometimes give you better bounds. And there is by Barnum, Sachs and Szegedy, there is actually an exact characterization of quantum query complexity in terms of semi-definite programming, but that's of course too general to be of good use. The real world. Yeah, why not? So,
there is no filter on your PC.
Well, there was something I wanted to say here, but I forgot. Oh yeah, but still, I think this polynomial method usually gives you quite good bounds quickly. And this adversary bound will give you sort of improvements. But usually within a polynomial, so within a polynomial, the polynomial method gives you the right bounds. So, and then you can sort of look at this more complicated, although this is not so complicated, techniques to get more precise bounds. So I do have something about the real world, because here is the real world, where we have NP and co-NP and P, and we have like these complete problems. And factorization, which isn't a decision problem, but could phrase it as such, is a problem that sits in NP intersect co-NP. I guess also this is kind of preaching for the already converted. And a big open question, which I think is very interesting, and I have no idea how to really prove it, is where does BQP sit in this picture? Does it so this factoring, it sits also in BQP, but it also sits in NP intersect co-NP. But are there things in BQP, for example, that are not in NP or not in co-NP? Where does this egg sit? Or are we really not that, is it really not that much of an interesting class, and is it really tiny? And is it only sit between P and NP intersect co-NP, or maybe does it even sit in P? All these questions are very interesting and not known. So it's not known exactly what where BQP sits. However, you can view this lower bound, the square root of n lower bound for the OR function, as evidence that NP is not in BQP. So you can transform that as constructing an oracle where NP is not contained in BQP. Because of course the OR is something that's easy for NP. And that just says that any proof that relativizes cannot demonstrate that NP is different from BQP. And my feeling says that it is just as hard as the general P versus NP question, the BQP versus NP question. We run into the same problems. So open problems I sort of alluded already. So can you improve these the relationships between